Okay, so we are talking about analyzing graphs of functions. We're going to talk about symmetry, even and odd functions, and then we're going to hit piecewise functions. The piecewise functions is like a whole new game, but we'll take it relatively slow and easy. So we're going to talk about symmetry. We're going to talk about symmetry with respect to the y-axis, the x-axis, and the origin. So you're going to see me use the WRT, which stands for with respect to. So we're going to have symmetry with respect to the y-axis first, and then we're going to have symmetry with respect to the x-axis. My handwriting looks terrible. And then symmetry with respect to the origin. So we're going to see all three of these. Wish I had more space up here. All right. So in this first example, if you look at this graph and you visualize your y-axis, you can see that this graph in blue has symmetry with respect to the y-axis because if you folded it, it would lie on top of itself. Now this graph is stagnant. We're not doing a reflection. We're not creating another graph. We are looking at a given graph, and it is already showing me symmetry with respect to the y-axis. So another example would be if I created one over here, and I'm going to look at the point 1, 2, and the point negative 1, 2, and I'm going to draw a parabola like this. And that's another one that would have symmetry with respect to the y-axis. I'm not reflecting anything. It is already showing me symmetry. But if I have symmetry, then that means that the point xy is on the graph and the point negative xy is on the graph. Because this would be like the point 1, 2, and this would be the point negative 1, 2. So when the x is positive and the x is negative, both of those points have to be on the graph. They both have to satisfy the graph or satisfy the given equation. So instead of just looking at it, if they give me an equation and say, does this have symmetry, we would have to check it algebraically by plugging in those 2 points. So for instance, if they give me that f of x equals x squared minus 2, and without graphing it, they say, does this graph have symmetry with respect to the y-axis? Well, to check it, I'm going to go ahead and take it out of function notation and just let it be y equals x squared minus 2. Both the xy coordinate and the negative xy coordinate have to satisfy this equation for it to have symmetry with respect to the y-axis. So the way you check that is you say, okay, the point xy gives the equation, really y replaced by y and x replaced by x, and there's no difference in the equation. So of course when you plug in xy, you're going to have the original equation. But if we come over here now to check this, and we plug in a negative xy, this is going to make the equation y replaced by y and x replaced by negative x. So it looks a little different. So this is going to become y equaling, well, a negative 1 squared is positive, so this is a positive x squared minus 2. If the equation remains the same, non-altered, in other words, if these two are the same, and they are the same, then yes, this equation, this function will have symmetry with respect to the y-axis. Any function that has symmetry with respect to the y-axis has a new name, and that name is that it is an even function. So if it proves out to have symmetry with respect to the y-axis, then it has a new name. It is named an even function. Okay, so let's try another example. Here's another question just like the one before. It says, does this function have symmetry with respect to the y-axis? Well, let's put a function up here. Suppose we have f of x equals x cubed plus 2x. Okay, so they're not giving me a beautiful little graph that I can just look at it and see if it looks like it has symmetry. They're giving me an equation. So the first thing I do is replace the function notation with y and then I try the 2 points. The 2 points have to satisfy the equation. Well, the xy is really the same thing, y replaced by y and x replaced by x, and it's going to give you the original equation. But if I plug in the other point, which is the negative xy, okay, which is that point on the other side of the y-axis, then this would say y replaced by y, but x replaced by negative x. And clean this up and see what happens. So this is going to be y equaling a negative 1 cubed is still negative 1. So this is a negative x cubed minus 2x. So when you compare now, these are not the same. So if they're not the same, then this function does not have symmetry with respect to the y-axis. So the answer is no, and it is not an even function. No symmetry and not an even function. Okay, no symmetry and not an even function. Okay, so here's one more. Suppose we have this one that looks like it could be hard. The absolute value of x minus 2. Okay, that does not look very fun, but you're going to see that it's not going to be difficult. So go back to the routine, replace it, and let's put it into an equation format instead of function format, which makes it a little easier. And of course, our xy, goodness, lots of people sneezing today. Okay, our xy is going to be replace the y with y and the x with x, and so you're just going to have the original equation. But the big one we want to check is when I replace x with negative x, which is where it's going to be on the left side of the y-axis, what does this become? Y replaced by y and x replaced by negative x. Okay, so this is y equaling, well, the absolute value of a negative number is going to be positive, right? So this is just going to be still the absolute value, and so it's going to work. These will be the same, and so the answer is yes, this is an even function. All right, so that's symmetry with respect to the y-axis. Okay, we're not reflecting. It's going to be just a graph that we look at and state yes or no, it does have symmetry with respect to the y-axis. So now let's look at symmetry with respect to the x-axis. Well, an example of this would be something like, let me put a couple of points on here. This would be an example of something, a graph already given to me in which it shows symmetry with respect to the x-axis. In other words, if you folded it on the x-axis, it would lie simultaneous with itself. It would coincide with itself. So this one has symmetry with respect to the x-axis. So in this one, note, this is the point, what? 1, 2, 3, 2. And the lower one is the point 3, negative 2. So my x, y, and what is the other ordered pair? X negative y. Both of those points would have to satisfy the equation. Both of those points would have to be on the line, meaning they would have to satisfy the equation of the line. Okay, so these look a little bit different. These equations, when you have symmetry with respect to the x-axis, are going to look a little different. So for instance, if this is your equation, x equals y squared plus 4. Now notice, I did not put f of x here. And the reason, and I cannot use f of x here because this is not a function because it will not pass the vertical line test. So these are not functions, these are just equations. But I'm checking to see if it has symmetry with respect to the x-axis. Okay, so to do this, the ordered pair xy would satisfy the equation, which is the original equation itself. But the other point I have to check is x negative y. So this is the one where it really gets interesting. So x is replaced with x, but y is replaced with negative y. Well, this becomes x equaling negative 1 squared is positive, so that's a positive y squared plus 4, and these are the same. And since they're the same, that means that both of those ordered pairs satisfy the equation. Therefore, yes, it does have symmetry with respect to the x-axis. Okay, so let's try another one. Again, I cannot put these in function notation. Okay, so suppose I have y equaling the square root of x minus 2x. This is just doing a lot of algebra. If I had a nice graph, I could almost tell you. Okay, so my first option is just to leave it with xy, which is really just the original equation. So where it gets interesting is if I have it so it has symmetry with respect to the x-axis, that's where y is replaced by negative y. And that's going to create the equation y replaced by negative y and leave the x alone. X is just replaced with same ox. So algebraically, this becomes negative y equaling the square root of x minus 2x. But as before, we don't like that negative on the y. So let's get rid of the negative by dividing by a negative 1. What color am I in the mood for today? Okay, so let's divide everything by negative 1. When I do that, this equation then becomes positive y, a negative in front of the radical, plus 2x. So now we compare, and they're not the same. So the second ordered pair did not satisfy the equation. Therefore, it does not have symmetry with respect to the x-axis. Okay. So now let's talk about another symmetry, which is symmetry with respect to the origin, which does have a name. It is a function. They call it an odd function. Well, you can see the image here, and when we talk about symmetry with respect to the origin, then we're talking really about a twofold situation. So if I look at the right half of the graph, and I first fold it over, I don't know if I can do this image. Maybe I should do my own image. That one is a really good example, but maybe I should do my own image. Suppose I do something a little nicer like this one. Okay, I'm going to do a nicer one first, and then we'll look at the one given and be able to say, yes, it does have symmetry with respect to the origin. Let's just look at this one. To have symmetry with respect to the origin is a twofold process. So in other words, if I begin by taking my graph and I fold it over the y-axis, which would make it look like that, and then I take that blue dotted line and I reflect it over the x-axis, then it would lie on top of itself. So it's a twofold process. If I fold it over the x and then the y, or over the y and then the x, and it comes back to itself, then this one has symmetry with respect to the origin. So if I take the bottom over here in quadrant 3 and reflect it, if I reflect it over the y-axis first and then over the x-axis, I'd come back to itself. So it kind of returns, it becomes simultaneous with its own graph when you do two reflections, both over the x and over the y. So when this occurs, if you have a point up here, suppose that point is the point, and I'm just going to make up something, 2, 8, then when you reflect it twice, if it comes over the y-axis first, it's a negative 2, positive 8, and then if it comes down, what would it be? Negative 2, negative 8. So when you reflect over both, or you show symmetry with respect to the origin, you're going to have x, y, and negative x, negative y. A twofold process to give you symmetry with respect to the origin. So the red line now if you reflected it twice, or if you just kind of somehow see a point here, this is a beautiful graph, but goodness, it makes it difficult to get a point. Let's look right here. This point right here. Let's just claim that point. Let's just claim that point as if it's a 2, 2. If you look over here, then you'll see the point -2, -2. So that one is going to work. All right. So if we want to, if someone just gives me an equation and without a graph, and they say, does it have symmetry with respect to the origin? So these should be functions. So I'm going to put it in function notation again. X to the 5th plus 3x cubed minus 3x. They're asking me about this one, so I'm going to take it out of function notation and write it as y equals. Okay, so I have two ordered pairs to check. Okay, the first one is just xy, and that is going to just return it to the original equation. The other one, which is the one we're really testing, is the -x, -y. Okay, so here's where we have to have a little algebra. So if I replace y with -y and x with -x, it'll look something like that. Boy, there's a bunch of negatives, so be very careful. So this is a -y equaling, a -1 to the power of 5 is still negative. So this is -x to the 5th. A -x cubed is still negative, so that's really a -3x cubed. And then a negative times a negative on the end is a positive 3x. Have to be very careful with your signage. Now the negative is on the left side, so I'm going to divide everything by -1. So it says y equals, so I can really compare the two equations. So this is going to be y equaling a positive x to the 5th plus 3x cubed minus 3x. So did this work? It sure did. It worked. So since they are the same, then the answer to this question is yes. And if you have something that has symmetry with respect to the origin, it is named an odd function. Symmetry with respect to the x-axis is not a function, so it doesn't get a nice name. But if it has symmetry with respect to the y-axis or symmetry with respect to the origin, it is renamed either an even or odd function. Okay, so now we're going to have some combined examples, and this is the questions you'll see. It'll say, and here's a little summary. If it's an even function, xy and -xy will satisfy the equation. If it's an odd function, xy and -x, -y, those are your functions, okay? And so it'll ask the thing, given this function, is it even, odd, or is it neither even nor odd? That's how the question will be asked. And then they'll give you an example like this. So they give me this function. And they're not asking about symmetry with respect to the x-axis because that's not a function. So we're only looking at this point really of symmetry with respect to the y-axis or symmetry with respect to the origin. Okay, so xy is just my original equation, and I'm just going to make it a y equals instead of, I'm going to take it out of function notation. Okay, if I want it to check it to see if it's even, if I'm checking to see if it's even, an even function, which would be symmetry with respect to the y-axis, what point am I supposed to check here? What ordered pair? -xy, right? So if it has symmetry with respect to the y-axis, it's in quadrant 1 and quadrant 2, so that's x and -x. Okay, so this would present y replaced by y and x replaced by -x. So cleaning it up a little bit, this is y equaling, okay, negative 1 squared is positive. And this would be my result. So did that work? Not the same, right? So it's not even. Okay, we just checked it, and it is not even. Okay, so let's check odd. Odd is symmetry with respect to the origin. So what is this ordered pair point going to be? Negative x and negative y, both of them. Okay, so this is going to come out to be, look up here at your original. Okay, here's your original up here. Here's my original. All right, and then we're going to come in here now, and we're going to take that y and replace it with negative y, and that x replaced with negative x. Y replaced with negative y and x replaced with negative x from the highlighted equation. And then I have to come in here and clean it up. So this is a negative y equaling, a negative 1 squared is positive, so this is a positive x squared minus 6x plus 9. I've got to get rid of the negative, so I'm going to divide that negative 1 off. And some of you multiply, which is fine, but every term, you must do the same thing to every term. So this becomes y equaling a negative x squared plus 6x minus 9. So is this an odd function? No, crud. So it's neither even nor odd. Okay, so this would be neither even nor odd. So it's not either of those. We could even write this. Neither even nor odd. That's how they write it. Okay, so let's do another example. A lot of algebra there. A lot of working with signs. Okay, so they're going to give me a function. They're going to say, is it even or odd, or neither even nor odd? And they're going to ask me this one. Suppose f of x equals a negative x squared plus 6. Okay, so I'm going to write my original function. I'm going to take it out of function notation and write this as y equaling a negative x squared plus 6. This is just a colon I'm putting there to separate so I can see the difference in my equations. Then if I want to check to see if it's an even function, what am I checking? This is over the y-axis. Negative x, there you go. Okay, instead of memorizing it, try to visualize it. Okay, try to visualize it. So y replaced by y, but x replaced by a negative x. But don't forget there's a negative in front of it. So this is y equaling a negative in front of, negative 1 squared is positive. There it is. Did it work? It sure did. Now there are cases where you can be even and odd. That does happen, not frequently, but it does happen at times. So we're going to say yes, it is an even function, but let's go ahead and check and make certain it's not odd also. So if it were going to be odd, then negative x, negative y, that's a 2 reflect process. Okay, so this would be replace y with negative y. Okay, so here's the equation I'm working with that I'm replacing. There it is. So I'm going to have y replaced by negative y, and x replaced by negative x. Okay, so this is negative y equaling a negative. Well, a negative 1 squared is positive. So this becomes a negative y equaling a negative x squared plus 6. But I've got to get the negative off of the y. So here's where I divide everything by negative 1. And so I have y equaling a positive x squared minus 6. This did not work, did it? Not the same. So it is not even. I mean, not odd. It is even, but it is not odd. So the answer to this question would be an even function. Okay, so it has symmetry with respect to the y-axis.